Welcome back to ECE 220. We are almost halfway through the labs. There's 5 sections. Section I goes next Tuesday. E, F, G, and H are this week. Today should be section G going into the lab, and I forgot to close the door, so I will quickly, as we're talking about announcements, hopefully you're getting PSpice up and running, and hopefully you can hear me when I leave the classroom. That might be interesting. I can lecture from my office. You guys just have to pretend I'm sitting or standing in the front. PSpice is due this Friday. You need to bring it to class. If you're going to lab, make sure you have your cat card, closed-toed shoes, and you're ready to take notes. Homework 3 is what will be the final material for exam number 1, and that's due Tuesday. Homework 4 hopefully will become available soon, but we'll be talking about that topical material or information today in Chapter 4. Exam 1, if you want help, go to the practice exams via the link on D2L. We're starting Chapter 4 today, and the first thing that we'll look at is terminology. Then we'll actually just start working some examples. Instead of trying to explain all the definitions and the terms, let's just start using the procedure, which is node voltage analysis, and then as we need it, we'll start to hopefully realize, oh, we need to sort of keep track of certain terms or definitions to help us work our way through. We'll look at a couple of examples, then we'll discuss different circuit configurations that give rise to finding a current, a branch current, differently when we are writing these. Essentially, we're writing Kcl equations at various nodes in the circuit, and there may arise different scenarios, and we need to get comfortable with how we approach each of those scenarios. That's what I'm meaning by discuss different cases for finding a branch current. Then we'll look at 2 more examples of performing node voltage analysis. And in this process, we are going to be selecting a reference node or a common, and we'll probably just indicate it by a ground symbol in our circuit. Does it matter how we select that reference node? Obviously, my analysis would differ from your analysis, but the results should be consistent. I may get different voltages because I've labeled my circuit differently, but if we compared those results properly, we would be getting exactly the same analysis of the circuit. That will hopefully become clear as we go. Chapter 4 really is giving you some very basic, some very fundamental strategies for analyzing circuits. And I'm putting in parentheses with resistors. That's what Chapter 4 is dealing with. But if you understand this strategy or these strategies, you'll be able to apply them in your next course, ECE 320, when we generalize from resistors to impedances, where now we have inductors and capacitors floating around in the same way that we have resistors moving around in our circuits. Now we'll be able to use these same strategies with Z's instead of R's. Or we'll expand from R's to Z's. So in parentheses, I'm saying with resistors, that's really what you're playing with in Chapter 4, but the strategies themselves are universally applicable. And this first set of material in Chapter 4, we will talk about node voltage analysis, NVA. And that's what I'm labeling Part 1, and I'm thinking on D2L, this will probably be Unit 4, is node voltage analysis. Chapter 4 will be distributed across several units in D2L. Chapter 4 gets into mesh current analysis, MCA, and it also does some source transformations and maximum power transfer. So we'll have more material in Chapter 4 than what you might find in Unit 4 on the course website. Let's start by quickly looking at planar and non-planar circuits. And you're going, well, they're all sketched on a plane. A plane or a train? No, this is not a flying plane, but a plane that we're drawing on, sketching on. The top two, A and B, those are exactly the same circuit. It's just that we've pulled one of those, morphed one of the wire connections, R7, to be outside of R2 and R3. And so you can see, even though it looks like they overlap, now you can see that, oh, I have, we'll call them meshes, little picture windows that don't have any crossing wires in them. The top two figures are what are referred to as planar networks. So that's this. This is figure 4.1 in the textbook, A and B. Hopefully you can see that A is the same as B. Even though it looks like, oh, we have some crossing going on, we can actually redraw that appropriately by morphing a wire or stretching and compressing a wire in the appropriate way so that we do not have any crossing lines. That's a planar circuit. And that, well, is in contrast to a non-planar circuit, which is the bottom circuit. This is now figure 4.2. And you see, no matter how you sort of pull and stretch wires in figure 4.2 or in circuit associated with figure 4.2, you're going to have some crossing occurring. You can't eliminate it. That's now, you can't draw it on a plane and not have some of the wires not crossing. In a planar circuit, you can do that. You can draw this on a plane and you don't have any wires crossing each other. That's a planar circuit in contrast to a non-planar circuit. Why does this matter? It matters because we can apply both of our strategies that we will be learning. Mesh current analysis and node voltage analysis can be applied to planar circuits. But mesh current analysis, which is the next analysis strategy that we will look at, cannot be applied to non-planar. So we can only apply node voltage analysis to both, and that's the strategy we're learning today, is node voltage analysis. Meaning, if you have a non-planar circuit, you automatically know what analysis strategy you need to apply. You can't even apply mesh current analysis, so don't even worry about it. Let's now focus on node voltage analysis. And I'm using these phrases to something that you don't feel comfortable with or maybe haven't used yet. We'll get into that today. But before we do that, we need some more terminology. All of our circuits so far have been planar that we've played with in this class. We haven't worried about non-planar circuits. Figure 4.3 tries to give us a generic figure that allows us to identify certain terms that we will be using throughout the rest of the semester in our analysis process. I think everyone's comfortable with a node. The nodes are labeled A, B, C through G on the network or the circuit in figure 4.3. Some of those nodes are not essential. What does it mean to be essential? And that's the second row in table 4.1. An essential node is a node where 3 or more circuit elements join. If that's the case, can we identify some essential nodes in that circuit? And there you're just counting elements that are connected to a particular node. If we look at node A, is that an essential node? There's just 2 elements that are connected at A. A is not an essential node. That doesn't meet the definition. What about B? Is B an essential node? An essential node says we have 3 or more circuit elements that are joined. We count those. We have R1, R5, R7, and a current source joined at B. That is an essential node. What about C? Node C. Is that node essential? Yes. So we can circle that one. What about D? Is D an essential node? No, there's only 2 circuit elements being joined by D, so D is non-essential. Do you see why it's not essential? We could effectively replace R2 and R3 with one resistor labeled as R2 plus R3. So we could effectively eliminate D if we wanted to. What about node E? Is that essential? I'm circling it. Yes, it is. We have 3 different elements being connected by E. What about F? No. G? Yes. So now we've identified the essential nodes. That wasn't hard. In a circuit. And once we have those essential nodes identified, now we can start playing with this circuit analysis strategy. Yes?
E and G, why have you circled the second node to the right?
So in B and G, why did I circle the second node? Because really that node is identical to the one that's labeled G or B. You can just collapse all of these down. So they have explicitly, and PSpice will do this as well, it'll start identifying where you have connections with dots, and sometimes that's redundant. So the dot to the right of B and G is redundant, but it's telling you those wires are connected. But you could glob all of those together. If you were soldering everything that I have in this big blob, you wouldn't want to make a soldering blob, but you could connect all of those pieces together and have one node. Even though it's identified as, well, there is a connection. Yes, it is a connection, but that's the same node technically as what G is labeling to the left. Are we clear on that? The fact that I've circled maybe some of these connections to establish the connection, which is critical, it still is all the same point. If we measured the voltage dropped between those 2 bottom dots, what would we measure? If you went into the lab, did you measure some things yesterday? I had to leave. I didn't have to, but I left. They kicked me out of the lab. I did have closed-toed shoes on. I didn't turn in my cat card, though. But I knew I probably wouldn't claim it if I turned it in. Do I ever yeah, I do use my cat card to get into places. Buildings, not movies or something. What? Where was I? Let's measure the voltage between those 2 dots. What is it? 0. So it's the same point electrically. All right. So we have quite a few more phrases to worry about, but let's move on because we can start playing with just essential nodes. here's the first example, and I'm calling this a basic node voltage analysis problem. And let me label some of these resistors. This one is 1, this one is 4, this one is 4, and this one is 8. Our first step, and we'll maybe make this a little bit more official as we go, but now I'm just being a little bit loose with the steps, but you'll see in the front cover, yeah, in your electronic, in your e-book, you have a cover, but in the front page of your book is this table of the steps involved in node voltage analysis. Now that you're sketching that circuit, the first step in this analysis is to identify the essential nodes. And I want you to help me with that. Is the node between the 10 volt source and the 1 ohm resistor an essential node? No, because I just named 2 elements. I didn't name more than 2. That's not essential. What about the 144 node? Is it clear what I'm meaning by that? So that is an essential node. What about the 428? What about the bottom? All of those are nodes below each of those elements. That's obviously essential because 4 things are being combined. How many essential nodes did we identify? 3. We need to pick one of those as our reference. In the lab, did you have, you maybe ran out of cables, but you were supposed to have a red cable and a black cable. The black cable usually is the common, or the ground, and the red is the one that you're measuring things with respect to the black. So here we need to identify a reference node or a common where we would connect our black cable in the lab, and typically it's the one where everything more nodes are associated with. And a lot of times in this class we draw it to where the reference node is going to be on the bottom. Let's just make this bottom node our reference or common node, and we might indicate that by this symbol, a ground type symbol. This is now our common or reference node, and everything that we measure now with the red lead is referenced to that black lead that's connected to that node on the bottom. Is that clear? That means that this leftmost node we could label as V1, and the plus minus is the red-black connection, and the other essential node has potential or voltage V sub 2 relative to that reference node. The first step is to now identify the essential nodes and define node voltages. And this is node voltage analysis. We need to identify node voltages and then we can do the analysis. We've now identified two node voltages from 3 essential nodes, and these we just called V1 and V sub 2. Once we've done that, now we can do our analysis. Now we write equations that those V's have to satisfy. And we simply write a Kcl equation for each node that's associated with the node voltage, if we can. Here we will be able to. We'll now do step 2, which is to write our equations. And in the node voltage analysis strategy, that is Kirchhoff's current law that we're writing. Meaning, we now need to do KCL at, let's say, call it node 1. We need to sum this current, and that current. I've drawn those all in blue, and they're all leaving the node. Those now need to sum to 0 by KCL. Everybody comfortable with that? Now, let's find the current flowing from right to left through the 1 ohm resistor in terms of our node voltages and given voltages. Do you see why that node above the voltage source was not essential? That's 10 volts relative to our common reference node that we defined. We know what that is. We don't need to call it an unknown voltage. It's given to us by what we set the voltage source to equal. What are we trying to find? We're trying to find, should I label these? Let me call this I1, I2, and I3. I now want to find, or I'm now saying that Kcl at node 1 is really just I1 plus I2 plus I3 equaling 0. Because they're all three leaving. The algebraic sum of those currents is equal to 0. Now, why did I decide to have them all exiting? Just so that I'm kind of following a strategy, so that I feel comfortable with what I'm doing. I could have drawn those randomly and had I1 going to the right and I2 going down and I3 going to the left. That's confusing. Why stress ourselves? Let's just make them all exit, and then we can kind of have a cookbook strategy for measuring or writing the expression. So we have the essential node because that's now what we're trying to find the voltage at those essential nodes that are not the reference. So we're trying to find V1 and V2. In the lab, you could just go measure it and be done. We're trying to now do the analysis so that we can verify what we measured in the lab. And hopefully V1 and V2 will be consistent with what we would measure in the lab. That's the idea. Now we just apply Ohm's law to find I1, I2, and I3. What is I1 in terms of the node voltage and given voltages? We need the voltage dropped across that resistor from right to left divided by the resistance, and that will be I sub 1. And the voltage dropped across that resistor from right to left is V1 minus 10. We now have V1 minus 10 divided by 1. That's I sub 1. That's just Ohm's law. Now we're writing all of these as Ohm's law to find I1. And if that's not comfortable to you, you could actually apply a Kvl equation, which is really sort of what we just did. We did minus V1 plus R1 I1 plus 10 is equal to 0. And I1 is now V1 minus 10 over R1. That's where that came from. If you are saying, I don't understand what he did, I just found the voltage dropped from right to left across that resistor. The current is in the direction satisfying our, what did we call it? We gave it a 3-letter. I'm giving myself time to remember. I'm walking around. Passive sign convention. Do you remember that? Ohm's law and passive sign convention now says that I1 and that V, or V, is equal to RI1. And that V from right to left in that 1 ohm resistor is V1 minus 10, and that's what we verified over here with a simple Kvl equation. And we wrote that down immediately here. V1 minus 10 over R1, which was 1. Here's the really difficult one. Find I2. Not. That's Ohm's law, isn't it? What is I2 in terms of the node voltage V1 and the resistor that V1 is across? I2 equals V1 divided by 4, isn't it? Since V1 is Ri2 and R is 4, I2 is now V1 over 4. That's I2. What's I sub 3? It's the node we're at. We're standing on node 1. That's V1 minus where we're going, which is V2, divided by 4. That's the resistor. So I3 is, in unison, V1 minus V2 over 4 is equal to 0. Are we comfortable with that expression? That's one equation that we wrote KCl at node 1 with respect to. We could clean this up a little bit if we wanted to by multiplying by 4 just to clear the fraction. We now have V1 times 4 minus 40 plus V1 minus V2 equals 0. Or we have 6 of the V1s minus V2 is equal to 40. That first equation gave us one equation in terms of the two unknowns, V1 and V2. We need a second equation because we have two unknowns, and that's why we're going to now write KCl at node 2. And this is, I think, where students struggle. Now I'm going to define another current there. I'm not going to call it minus I3. That's just going to confuse me. I'm just going to call it a new current going from right to left out of node 2. And I'm going to sum all of those algebraically and set them equal to 0. Let me call this one I4. Let me call this I5 and this I6. Just to give me some unique labels on those currents. That's not really necessary, but I'm really walking through slowly so that it's clear where all of this is coming from. Using our strategy from before, what would you say current I sub 4 needs to equal? It's where we start, node 2, that has a potential or a voltage of V sub 2. We subtract from it where we're going, which is V sub 1. That's the drop from right to left across that resistor. And we divide by that resistor, and we have our current I sub 4. For 2, we're saying I sub 4 plus I sub 5 plus I sub 6 is equal to 0. We are now trying to find I sub 4, and I sub 4, I said, was V2 minus V1 over 4. What's I sub 5? It's given to us, isn't it? As a source, it's 2. We just write it down. Doesn't involve V sub 2, it's just 2. I sub 5 is 2. What's I sub 6? It's not 6, it's I sub 6. That's V2 over 8, isn't it? Ohm's law. And that equals 0. We can clean that up if we want by multiplying everything by 8. You have 2V2 minus 2V1 plus, what did I multiply by? 8. 16 plus v sub 2 is equal to 0. Or, that now says I have minus 2v1 plus 3v2 equaling minus 16. Obviously, I'm walking through this with more steps than what I was anticipating. But is it clear now where those two equations came from? Now we simply, step 3 is to solve for the unknowns. Step 3 is to solve those equations. We have minus 2 v1 plus 3v2 equal to minus 16. And the first equation, well, can I multiply that by 3? Because now I know I want it to cancel the 6v1. Let me write this one down first. 6v1, this is the first equation we derived, minus v sub 2 is equal to 40. The second equation is in the black box here. We're going to multiply everything by 3, and I get minus 6v1 plus 9v2 is equal to minus 48, or 3/16. Now I've got two equations, two unknowns, and I've rewritten it. I didn't change anything by multiplying everything by the same number. I can now combine those, and I have 8v2 is equal to minus 8. Wow, that was easy. V2 is actually minus 1 volt relative to that reference node. What's V1? We can just use one of those equations to solve for V1. And which one do I want to use? Can I use, doesn't really matter. Let me just use this one that's right there so that it's clear. It's now minus 2v1 plus 3 times v sub 2, which is minus 1, is equal to minus 16. Or I now have minus 2v1 equal to minus 13. Or v1 is 13 over 2 volts, or 6.5 volts. That's example 1. Clear on that for node voltage analysis. Let's try another one. And I'm going to scroll quickly so you didn't see the answer. But let me label this. This is now a 10 ohm, a 1 ohm, a 2 ohm, a 3 ohm, a 4 ohm. And you know the drill. We need to find essential nodes. Can we identify essential nodes in this circuit? Quick answer is yes. Now we have to do it, right? Two elements being connected, is that an essential node? No, not by definition of essential node. So here's an essential node. Here's an essential node. Here's an essential node. And here's an essential node. How many essential nodes do I have? 4. I need to pick one of those as my reference that I will now connect my black lead to in the lab. That's my reference node. That's my common node. And just the way we learn circuits, we typically feel more comfortable putting the common node close to the bottom, and I'm just going to put it underneath the 12 amp current source. That's going to be my common node. We'll show that it doesn't matter. It doesn't look like that's going to be today, but at some point we'll maybe show it doesn't matter where we pick the reference node, we just pick one and work the problem. It will obviously give us a different collection of voltages, but your voltages and my voltages will be consistent or compatible. Here I'm going to just make this the common or the reference node. So I've now identified my essential nodes. Now I need to define, basically label, voltages relative to the common node, or where am I going to connect my red lead? I'm going to connect it to each of these blue highlighted nodes, my essential nodes, and how they get labeled is somewhat random, but let me just say that this one is what I'm going to call V1. The red cable is now where the positive is. It doesn't really matter if you called that one V3 and somebody else called it V2. Well, you can't switch the negatives and positives once you've defined your common node. So once you've defined your common node, that's always going to be the negative terminal of your voltage that you're measuring with respect to. So the common node is always going to have the negative sign associated with it. Now, if V1 ends up being negative, then obviously the polarities were not as you had them labeled, but your labeling is consistent with what you measured. The next one I'm going to label is this one, and I'm not sure how I want to make it clear, but there's the plus, here's the minus, and this I'm going to say is V sub 2. It's not the voltage dropped across that vertical 1 resistor, it's the diagonal voltage across the 2, 4 and the 1, 3. Is that clear? That voltage V2 is from the common node up to, I'm reaching across diagonally to V sub 2. V2 is not the voltage across that 1 ohm resistor. Is that clear? How would I find, well, this is kind of getting aside, but can you find the voltage across that 1 ohm resistor in terms of the labels I've attached to the circuit now? From top to bottom, it's just V2 minus V1. That's the voltage dropped across that 1 ohm resistor, going from top to bottom. What about the last essential node? Well, obviously we're going to call that V sub 3, and there's the plus and there's the minus. I've defined V1, V2, V3. Do you see that somebody could have just completely shuffled those, and somebody might have called the bottom one V3, and the top one on the left V1, and the other one V2? That's okay. You just have to work your problem, and then your V's would not be equal to my V's, but they would be consistent. Is that clear? We've now defined V1, V2, V3 to analyze this circuit. What's the next step? Now we just write Kcl equations at each of those nodes, node 1, node 2, and node 3, the way that I've labeled them. So now I write Kcl equations. And at node 1, what am I doing? I'm going to just continue to write them out of the node. Those are the currents. I have 3 currents leaving that node. The one going to the left is what? That's just a given value. That's what the current source is set at. That's 5. So my very first current is 5. What's the one going straight up through the 1 ohm resistor? Now I want my positive label on that to be at the bottom of the resistor. That's where I'm at. That's V sub 1 minus where I'm going, which is V sub 2, and divide by the resistance. Ohm's law is telling me the current going vertical is V1 minus V2 over 1. What about the current going to the right? That's V1 minus 0, or just V1, divided by 3. So if we combined all of these together, I have 1 plus 1/3 V1 minus V2 plus no V3 equal minus 5. Anybody taking linear algebra? We're going to do some linear algebra to solve this. We're going to put it in a matrix. That's why I've written it so structurally. V1, V2, V3 with coefficients equal something. Now I have 1 equation and 3 unknowns. I need 2 more equations, and I'm going to find those by writing 2 more Kcl equations. The second Kcl equation is now relative to node 2. So let me say that it's that current, this current, and that current. And what I hope you're not getting all twisted and confused about is that, well, in your last Kcl equation, you wrote the current going up. Now you're writing it down. Just put that aside and just worry about the red for now. And just write it consistent with the red labels. Are we okay with that? That we have to be comfortable with. Now, the current going to the left out of node 2 is what? Is it V1 minus 5 divided by 10? No, it's not. That 5 is a current source, isn't it? It's not a voltage source. That current going to the left is actually minus 5. It's going counter to how 5 is actually going. We see that? The current going to the left is now minus 5. What's going down? It's where we are, V2, minus where we're going, V1, divided by 1. What about the current going to the right? It's where we are, V sub 2, minus where we're going, V sub 3, divided by 2. If we multiply everything by 2, we have minus 10 plus 2V2 minus 2V1 plus V2 minus V3 is equal to 0. Or, writing that in our linear algebra form, we have minus 2V1 plus 3V2 minus V3 is equal to 10. Actually, I didn't want to do that. Let me just keep it, because I didn't do that before, did I? Let me just, so you can see where these numbers are coming from, let me just say this is now minus V1 plus 1 plus 1/2 V sub 2 minus 1/2 V sub 3 equaling 5. It's going to be the same, but now it's hopefully clear where these coefficients are coming from. More clear than by me multiplying through by a certain number. You should be able to follow the coefficients as they are placed in that second equation. What about 3? Node 3. Node 3, I have this current, I have that current, and I have that current. The current going to the left, V3 minus V2 over 2. Plus the current going down, the left current going down. That's just V3 divided by 4. Plus, now that's going opposite to how I have my current labeled. It's just going to be minus 12. And all of that equals 0. So that now I have 0 V1 plus or minus 1/2 V2 plus a 1/2 plus a 1/4 V3 equaling 12. And now next year when you take 310, that's a linear algebra class in ECE. If you're taking the math version and various numbers, now we just compile these 3 equations, blue, red, and black, into a matrix structure. We have some matrix times our unknown vector of voltages equaling the right-hand side. And the right-hand side is minus 5, 5, and 12. I don't know why I'm trying to get so color-coded, but you see what I'm doing? And the blue, the top one, was 1 plus 1/3, minus 1, and 0. The middle one was minus 1, 1 plus 1/2, and minus 1/2. And that's just row times column for the different rows. The final third row, I had no V1s. I had a minus 1/2 scaling V sub 2, and I had a 1/2 plus 1/4 scaling V sub 3. And now I can just invert that matrix, and I have my V1, V2, and V3. What do I have? I have something times a voltage equals a current. So here's a voltage. What are the dimensions on that voltage? Or that matrix of voltages? How many rows? 3. How many columns? Of the V, has 1 column. It's a 3 by 1 matrix. What about this bad boy? Something times V gives me currents. That's the reciprocal of resistors. This is actually a G matrix, conductance, and it's 3 by 3. And this is I, 3 by 1. It's a current and it's a matrix. Couple of notes, and I'll maybe put these in after we close. One is, what happened to our 10 ohm resistor? Is it sprinkled anywhere? I've tried to keep all of our coefficients in play by not scaling anything. What happened to that 10 ohm resistor that the current source was going through? Oh, and isn't that G matrix nice? What do I mean by nice? Well, it's symmetric. It's symmetrical, right? If you flipped it across the diagonal, you'd get the same thing. Why? Because I didn't have any dependent sources in my circuit, the G matrix will be symmetric. The other point that I was trying to make was concerning that 10 ohm resistor. What's our ideal current source say? I'm going to give you 5 amps no matter what that 10 is. You told me to be 5. You put a 20 there, and I'm going to still give you 5. So that 10 was irrelevant. We have a resistor in series with a current source. Don't worry about it. It's not impacting your analysis. We can have the dual of a voltage source in parallel with a resistor. But that's enough for today, although we only got through 2 of the 4 and all the other. So we'll pick up there tomorrow. We're going to have a great day tomorrow. Don't forget your P-Spice homework. It's due in class.